in this video we're going to set up iterated triple integrals to find the average value of a function on a region, and we've got the graph of the region here. So even though we have the graph of the region, we should make sure that we understand which equations are which parts. I have z equals 3x squared, so that is a parabolic cylinder, extends parallel to the y-axis. The generating curve would be z equals 3x squared. So that would be the parabolic cylinder that opens up. And then I have z equals 4 minus x squared. That's another parabolic cylinder, which would extend parallel to the y-axis. That one would have a vertex at z equals 4 and open downward. So that's going to be this one here on the top. Y plus z equals 6. That is a plane. And that plane would also be like a cylinder. It would extend parallel to the x-axis. So that's going to be this plane here, which goes parallel to the x-axis. And then y equals 0 would be the xz plane, so that would be here on the back side. So even when the picture is given, you want to make sure that you understand which equation goes with which surface and how those are oriented with respect to the axes, so that you can think about whether your region is x simple, y simple, z simple, all of the above, none of the above, whatever. Okay, so we're going to do average value. We did average value with double integrals before, and so the idea is basically the same here, just going to extend that. When you think about the average value of the function, and again, I've just used that notation borrowed from statistics there to indicate the average of something, you're going to think about the sum of that function. That's what an definite integral is. So in this case, we've got a function of 3 variables, so that would be a triple integral of our function over our region. And then we're going to divide by the size of the region. So for a 3-dimensional region, that would be the volume of the region. Okay, so we're going to go ahead and set this up. Our function that we're integrating is a polynomial function, which is continuous everywhere. So don't run into any trouble with continuity or definitions or using Fubini's theorem. So it's really just a matter of thinking about our region, whether our region is x simple, y simple, z simple, and then going ahead and setting up our integral. Okay, so let's look at the region here and think about whether the region is x simple. So if I draw lines through the region in the direction of increasing x, and again, you want to make sure that you go all the way through the region, top to bottom, forward to backward, in the direction of increasing x. So when I go through that region in the direction of increasing x, if you thought about the region and the shapes of the surfaces, you should notice that when I drew these lines near the bottom, I would be entering along the back side of the cylinder z equals 3x squared and leaving along the front side of that cylinder. So I'd be entering and leaving through the two sides of the parabolic cylinder z equals 3x squared. But when I'm at the top here, when I drew these lines in the direction of increasing x, so parallel to the x-axis up here near the top, I'm entering through the other parabolic cylinder, z equals 4 minus x squared on the back side, and then leaving through that on the front side. So this region is not x simple, because sometimes I'm entering and leaving through one surface, and other times I'm entering and leaving through a different surface. If I absolutely had to do this integral with setting dx up on the inner integral, I could do that. I could split it into 2 separate regions at the place where it switches. So I would have one integral set up over the bottom where we enter and leave through z equals 3x squared, and then another integral set up over the top part where we enter and leave through z equals 4 minus x squared. But if I can avoid it, I would prefer not to have to do that. So the thing to notice here is that this region is not x simple. Okay, if I want to think about this region and whether it is z simple, I want to think about going through the region in the direction of increasing z all through the region. So all along the y, all in the x direction, going through that region in the direction of increasing z. And you should notice that that region is also not z simple. When you go through the region in the direction of increasing z, you're always entering through the parabolic cylinder that opens upward, the z equals 3x squared parabolic cylinder, but you leave through different surfaces. So when you are at kind of the left edge of this region, you're leaving through the parabolic cylinder z equals 4 minus x squared. But when you're farther to the right, along the y-axis, you're going to be leaving through the plane y plus z equals 6. So the region is not x simple and it is not z simple. So let's check for y simple. So I'm going to think about going through the region in the direction of increasing y all through the region parallel to that y-axis. And the key here is noticing that these two parabolic cylinders extend parallel to the y-axis. So when I go through that region in the direction of increasing y, I'm never entering or leaving through either of those parabolic cylinders. When I go through in the direction of increasing y, I'm always going to be entering through y equals 0 at the back side, and then I'll always be leaving through the plane y plus z equals 6 along the front side. So this region is y simple. Okay, so we're going to go ahead and set up our integral here with dy on the inner integral. And the function that I'm going to integrate, don't want to forget to write that down. And we're going to do dy on the inner integral. So as I go through that region in the direction of increasing y, I enter at y equals 0, and then I leave through y plus z equals 6. I need that solved for y, so I'll have y equals 6 minus z. All right, and then to set up my outer limits of integration for that, I want to think about that region in the xz plane. So I'm going to collapse my 3D solid back into the xz plane. And again, the key here is recognizing that those parabolic cylinders go parallel to the y-axis. So when you collapse that back into the xz plane, you're really just going to end up with this region that I just filled in blue back here, formed by the edges of those parabolas. So I'm going to draw a new little two-dimensional picture down here of that. Okay, so when I look at that region is not x simple for the same reason that the original region was not x simple. Sometimes you enter and leave through one parabola, and other times you enter and leave through the other parabola. But this region is, this two-dimensional region here, is z simple. So I'm going to go ahead and set z up next. So I'm looking at my two-dimensional picture here to set up these next two layers of integration. So I'm going to enter through z equals 3x squared, and then I'm going to leave through z equals 4 minus x squared. And then my outer integral, your outer integral should always have constants for those limits of integration. So if you look back at those Fubini's theorems that we did before, always have constants on those outer limits of integration. And how you think about that, again, you're just going to project back into the variable you haven't done yet. So I'm going to project down here onto the x-axis and look at that interval along the x-axis. So we'll need to figure out what these points are, where those two parabolas intersect, at least the x-coordinates of those 2 points. So maybe you can look at that if you can think about the graph. If not, you can solve a little system of equations. So you'd have z equals 4 minus x squared. You're looking for where that is equal to z equals 3x squared. So our x is going to go from -1 to 1. So there's our integral for the numerator. For the denominator, I'm going to divide by the volume of the region. If the region happens to be a region where you can just find the volume, maybe it's a sphere or a cylinder or a box, then you can just find the volume and divide by the volume. But if not, you can use an integral to find that. In this case, this is not a region that you probably know the volume of, so we're going to go ahead and set up an integral for that. Since the region I'm integrating over is the same, all of my limits of integration will be the same here. It's just that I'm integrating over a different function, in this case 1. All right, this problem just asks us to set up the iterated integrals, so I could stop there. If you actually needed to evaluate the integrals, there are some handy things to notice here. If you think about these integrals as sums, you might notice that some of this simplifies or is going to drop out. So if I think about our region, partition the region, choose points in each little box in the partition, and plug those points into the function that I'm integrating, you might notice that there's some part of this function where that integral will actually end up being 0. Not all of it, but some of it. So when I think about that, because of the symmetry here, for every point that I have on the front side here where I've got a positive x-coordinate, there's a point on the back side that has a negative x-coordinate and the same y-coordinate. So when I plug those points in, those partner points, the positive x-coordinate and the negative x-coordinate with the same y-coordinate, when I plug those points into this and add all those function outputs up, I'm going to get 0 for that part of the integral. So the sum of all of these function values on our region will be 0. Not on every region, but on this particular region, the sum of all of those will be 0. So if you actually have to evaluate this, it sometimes is helpful to notice those things, and it can save you some extra work that you could really just evaluate the integral in the numerator over the last term. Okay, so you want to be careful about that though. You want to be 100% sure that that really is going to drop out and not just neglect it and then realize, oh, you should have actually integrated that.